Hello, can you hear me, please? Hello, is there anyone who can hear me?
Yes, sir, we can hear you.
Okay, sorry, there is a little bit of an internet issue and I'm running up and down. I hope this should work. I'm on my own internet. So let us start. So let me share the screen. Can you hear? Can you see the screen?
Yes, sir.
Okay, thank you. So now, so far you have studied about how to design using Timber, and I mean, in the next few weeks, we'll see how can we use steel to construct or to design structures. So I mean, today I'm going to give you a bit of an introduction about uh, the steel structures and code, etc. And then from next week onwards, we will go into detail of the design using steel. Now, you might have discussed these points earlier as part of timber design. In any structural design, we have to base the design on few fundamentals. So those fundamentals are the basis of structural design. Now, any structure that is designed to withstand some load should have adequate structural resistance. So if you consider a beam, if you consider a slab, say if you consider a boundary wall, it should have the sufficient resistance to carry the force for which it is designed for. So it should have adequate structural resistance. Then it should meet serviceability requirements. Serviceability requirements mean that it should be usable during the service life of the structure. Okay, so it should be usable during the service life of the structure. Then it meet required durability. That means, say if you take a building, the building is designed for 50 years. So an office building or a house, the intended service life is 50 years. So during that 50 years, it should not face any durability concern. And it should have adequate fire resistance, and it should be robust to avoid disproportionate collapse due to damage from events such as explosion or impact and consequences of human. For example, if you have a bridge and a big truck hits a part of the bridge, means the bridge should withstand that impact. It may have some serious damage, but it should not collapse. So that is what it means to be robust. So these are the bases. Any structure, these are the bases that you have adequate structural resistance and you meet serviceability requirements, and it has sufficient durability, protection, and fire resistance, and to be robust. So these are the uh, points that or the basis or the requirement of structural design. So any material you choose, whether it is timber, whether it is steel, whether it is concrete, or whether it is masonry, all of them are designed on this basis. So when you design something on the basis of structural design, then you expect some service life, an indicative service life. So as per the Euro code, the indicative design working life means we expect a structure to satisfactorily perform the intended purpose or serve the intended purpose during that indicative design working life. And it should not demonstrate any serviceability concerns, and it should be usable. So if you take a temporary structure, it's 10 years, and say a replaceable structural parts, 10 to 25 years, agriculture or similar structures is 15 to 30 years, building and other common structures 50 years, and monumental building structures, bridges, and other civil engineering structures 100 years. This is as per the Euro code. And if you look at the British version of the Euro code, there are slight changes. If, for example, for bridges and monumental building structures, British code expect it to be serving 120 years. So those are the indicative design working life for any structure. Then if we move to the structural design, we have looked at something here. You know, the building should have adequate structural resistance, right? So how to define the resistance? Say the resistance of the structure for applied actions is governed using the basic equation. Now, if your resistance is that characteristic resistance is Rk, then your design resistance is Rk over gamma m. So gamma m is a partial factor which accounts for material, geometric, and modeling uncertainties, and is a product of gamma m into gamma rd. So if you have any material, say for example, if you take concrete, the design characteristic strength of concrete will be varying. It will be varying by a small margin. Say one batch will not be identical to the next batch. So considering these uncertainties in achieving the exact design resistance, there is a partial factor gamma m is introduced. This gamma m is always less than 1. So your design resistance is always greater than characteristic resistance. So characteristic resistance is, say if you do an analysis and you obtain a required bending moment, or you obtain required shear force. So then the characteristic resistance uh, is the value that you obtain from the analysis, and then the design resistance is a value that you obtain from characteristic resistance, and it is obtained by dividing the characteristic resistance by a factor called gamma m partial factor, which is less than 1. So basically we estimate the design resistance and we check the design capacity. So we'll see as we go on. Now if you take the material uh, factor, that gamma m, and say here you have gamma m and gamma rd. So this gamma m is these values. So for a timber it's 1.3, for glulam 1.25. So say for a connection 1.3, punched metal plate fasteners it's 1.15, and these are ultimate limit state and service limit state factors. For example, concrete, we have a gamma m value of 1.5. For steel, it is 1.15. So why concrete has a higher gamma m value than steel? Says steel is 1.15, concrete has 1.5. So why concrete has a higher value than steel? So is anyone who can tell me why concrete has a higher value than steel? Can anyone tell me why? I hope we have few participants. So any of you, can you tell me why concrete has a higher value than steel? Because concrete has the variance between each batch of concrete is high. Say one batch you might get 30 for, say you order a grade 30 concrete and you might get 31 megapascal for one batch. You might get 29.5 megapascal from another batch, and you might get 32 from another batch. So these are characteristic strengths. 29.5, 31 and 32 are characteristic strengths that we obtain by testing from the lab. So it varies, but if you take steel, the values are consistent. Say if you take one batch of steel, your yield strength will be 550, and the next batch also 550, because it is produced in a factory environment under highest quality control. So the variability in the quality of steel is less compared to concrete. So that's why the gamma m is 1.5 for concrete and 1.15 for steel. So if you consider this RK and when you divide this RK by gamma m, say this 1 over gamma m is becoming less than 1. Okay, so if your design characteristic resistance is 30, then when you have 1 over gamma m that is less than 1, means your design resistance is lower than the characteristic strength. Say, if you are receiving a batch of concrete which is tested for 31 megapascal, but your design value will be 28 or 27 or 24, it's less than that 31. The reason is we underestimate the strength of the material when designing a structure. So if the material can carry 550 megapascal, we might be designing assuming it can only carry 500 megapascal. So that is the design resistance. Now, when it comes to construction of steel, we are looking at steel. So when it comes to construction of steel, the steel was introduced in the 1956. So it became an alternative construction material to stone, brick, and timber, wrought iron, and cast iron, which were being used at the time. The advantages of construction steel: it possessed high strength and it possessed high stiffness, and more importantly, it possessed a good ductility compared to wrought iron and cast iron. So it was ductile, it was possessing high strength and high stiffness, and with relative ease of fabrication and cost-wise competitive as well. So that's why steel became so popular in construction, and there was a dramatic increase in the use of steel, construction steel as a construction material. Steel is most often used for structures where loads and spans are large, and therefore is not often used for domestic architecture. For example, in the house constructions or say 2-3 story building construction, steel is not used often because it has a good strength and uh, high load carrying capacity. So it is used in big structures. Say, for example, some of the tall buildings were constructed using steel, and even factory floors, factory buildings, and where you need a larger span, stadiums, etc., are constructed using steel. But there was no major interest in using steel for domestic architecture. However, with the introduction of cold form steel, this application is increasing recently, the use of steel in the domestic architecture. So the countries like Australia and the US and Europe, they have started constructing houses using cold form steel, which are very thin members and elements compared to the hot rolled steel. So steel is now again started being used in domestic architecture as well. The steel used in structural engineering is a compound of 98% iron and small percentages of carbon, silicon, and manganese, phosphorus, sulfur, niobium, and vanadium. Increasing the carbon content increases the strength and hardness, but reduces the ductility and the toughness. So carbon content therefore restricted between 0.25% and 0.2% to produce a steel that is weldable and not brittle. So what is more important is that we should produce something that is not brittle, because the cast iron and wrought iron were brittle and the construction steel were bit more ductile, and the reason why it is appreciated very much is because of its ductile nature. So ductile nature means that you might have studied this as part of mechanics of solids. When the material is ductile, it can yield. So yielding means it dissipates the energy. It dissipates the energy. So, uh, so therefore, uh, it is a ductile material, and to be ductile, we need to reduce the carbon content. The niobium and vanadium are introduced to raise the yield strength of the steel. The manganese improves corrosion resistance. Phosphorus and sulfur are impurities that we could not able to eliminate. Steel used in practice are identified by letters and numbers. For example, S3235 steel with a tensile yield strength of 235 MPa. Okay, so these are the type of steel. So if I mark a steel by S550, what does it mean? If I mark a steel by S550, what does it mean? Can anyone tell me? Hello, can you tell me what does it mean when I mark a steel by S550? Excuse me. Doesn't seem that no one is answering. So if you mark it by S550, that means that it is the steel has a grade of yield strength of 550 megapascal. So that's the meaning of 550. So the standard steel sections. So these are standard steel sections that is used in construction. Say you have a hello, can you see my screen? There is the message is coming on. Hello there. Anyone?
Yes, sir. Yes.
Do you see a message like please move this window away from the shared application?
Yes, sir.
Okay. Okay, so there are some standard steel sections is used in construction. So there is a section called universal beam. Actually, in the design, while doing the design, you will come across it's being labeled as UKB. Okay, so it is it's UB and UKB are same. Then there is something called universal column, that is UC or UKC. Then you have channel section being used, angles used, structural T from universal beams are being used, hollow circular sections, rectangular hollow sections, and bars, solid bars are being used, and plates are used. Sometimes plates are used to fabricate beams and columns as well. So if you look at the difference between a beam and a column, generally beam has a deeper web than the flange, and a column will have same size flange as well as the web. Okay, because it carries load axially and beams carry load transversely. So that's why the difference. Then application of steel and the steel sections. When a member is in tension, a round or flat bar is the obvious choice. However, a member in tension may be in compression under alternative loading, and an angle T or tube is often more appropriate. Say if you have a tensile force acting on a member, just purely tensile force, even a wire is enough, a steel wire is enough to carry that load. But if you have an element which is under tension during one cycle of loading, and if it is under compression during another cycle of loading. Yes, someone raise hand, please ask your question. Hello, I think Gunawardhana raised your hand.
Sir, we got another lecture.
Pardon?
10:30 we have another lecture.
Do you have another lecture now? Okay, so let me wind up with this slide, then we'll continue from next Monday. This week you will have the workshops with Dr. Somaratna, and next week we'll have our own workshop. So now if a structural element is bending about one axis, then an I section is the most efficient, because a large proportion of the material is in the flanges, that is in the extreme fibers. So you can see here the flange is thicker than the web. So generally if you look at the beam, flange is thicker than the web, because we want to keep the mass away from the central axis. So we'll discuss this further when we meet next Monday. I hope I'll sort out this internet issue on Monday. So we'll meet on Monday at 10:30. Thank you.